Welcome to everyone. I'm James Jensen, today's webinar chair. I am a contractor supporting the Office of Indian Energy Policy and Programs Tribal Energy Webinar Series. Today's webinar, titled Tribal Microgrids, Exploring the Why and How, is the 9th webinar of the 2020 DOE Tribal Energy Webinar Series. Let's go over some event details. Today's webinar is being recorded and will be made available on DOE's Office of Indian Energy Policy and Programs website in about 1 week. Copies of today's presentation slides will be posted to the Office of Indian Energy's website shortly after this webinar, if they're not posted up there already. Everyone will receive a post-webinar email with the link to the page where the slides and recording will be located. Because we are recording this webinar, all phones have been muted. We will answer your written questions at the end of the final presentation. You can submit a question at any time by clicking on the question button located in the webinar control box on your screen and typing your question. Unfortunately, Ms. Pierce, who usually provides the introduction on behalf of the Office of Indian Energy, is unable to join us today. Tweety Doe, a project officer with the office, will be giving the opening remarks. Tweety has served as a project officer with the Office of Indian Energy for the past 4 years. Tweety administers financial assistance awards to Indian tribes, Alaska Native villages, and tribal and intertribal organizations. Before joining the Office of Indian Energy, Tweety served for 8 years with the U.S. Department of Energy Office of Energy Efficiency and Renewable Energy as a project officer and as a program management analyst. Before joining DOE, Tweety worked with the Council of Energy Resource Tribes, where she gained valuable experience working with tribal leadership on energy and resource planning and management. Tweety has a Bachelor's of Arts degree in Political Science from the University of Washington and a Master's of Arts in International Studies with emphasis on economics and human rights from the University of Denver. Tweety, the virtual floor is now yours.
Thank you, James, and hello, everyone. I join James in welcoming you to today's webinar. This webinar series is sponsored by the Office of Indian Energy Policy and Programs, otherwise referred to as the Office of Indian Energy. The Office of Indian Energy directs, fosters, coordinates, and implements energy planning, education, management, and programs that assist tribes with energy development, capacity building, energy infrastructure installation, reducing energy costs, and electrification of Indian lands and homes. To provide this assistance, our deployment program works within the Department of Energy across government agencies and within Indian tribes and organizations to help Indian tribes and Alaska Native villages overcome the barriers to energy development. Our deployment program is composed of a 3-pronged approach, consisting of 1, financial assistance, 2, technical assistance, and 3, education and capacity building. This Tribal Energy webinar series is just one example of our education and capacity building efforts. This webinar series is also part of the Office of Indian Energy's efforts to support fiscally responsible energy business and economic development decision-making, as well as information sharing among tribes. It is intended to provide attendees with information on tools and resources to develop and implement tribal energy plans, programs, and projects, highlight tribal energy case studies, and identify business strategies tribes can use to expand their energy options and develop sustainable local economies. In today's webinar, we are focusing on microgrids, describing what they are and the benefits that they may provide to tribal communities. In addition to an overview of microgrid basics, we have 2 case studies which highlight why and how those tribal communities chose to develop microgrids. We hope this webinar and the series as a whole is useful to you. We welcome your feedback, so please let us know if there are ways we can make the series better. Before I turn it back to James, I personally thank the presenters, Jim, Kelsey, Alexandra, and Carl, for giving their time in preparing for and for presenting on today's webinar. Thank you all. And James, the virtual floor is back to you.
Thank you, Tweety. Before we get to the presentations, I will introduce all of today's presenters. For our first presentation, we will hear from James Reilly. Jim is an electrical engineer working in the engineering and modeling group of the National Renewable Energy Laboratory's Integrated Application Center. Jim's focus is on high renewable penetration in microgrids and distribution systems. In the last 9 years, Jim has worked with the U.S. Department of Defense and Department of Energy on large generator interconnection, microgrid design and optimization, and distributed wind research. Following Jim, we will hear from Kelsey Moldenki. Kelsey is a senior planner for the Quinault Indian Nation, where he handles long-term planning for the tribe, such as leading the Tahova village relocation effort. The Relocation Master Plan was awarded the 2017 Best Plan for Small Cities and Counties by the Washington chapter of the American Planning Association and the Washington Governor's 2018 Small Communities Award. In his senior planner capacity, Kelsey interacts frequently with community members regarding their desires for development on the reservation, as well as mapping, current planning, and grant writing. He holds a Bachelor's of Science in Planning and Development from the University of Southern California and a Master in City Planning from Massachusetts Institute of Technology. Our final presentation will be a joint presentation from Alexandra Salmon and Carl Hill. Alexandra Salmon was raised in the village of Igiagig, Alaska, located 250 air miles southwest of Anchorage in the Bristol Bay region, which covers 40,000 square miles, stretching across tundra and wetlands, crisscrossed with rivers that flow into the Bristol Bay. Up to 40 million sockeye salmon return to this watershed each year, making it the world's largest salmon run. Alexandra graduated from Dartmouth College with a dual Bachelor's of Arts degree in Native American Studies and Anthropology. After graduating, she returned to work for the Igiagig Tribal Village Council as acting administrator and as president from 2008 through the present. She also serves as a member of the Igiagig Native Corporation Board, as well as the Lake and Peninsula Borough Planning Commission, and manages several family businesses. She received a Master's of Arts in Rural Development in 2020 from the University of Alaska Fairbanks. In her work as president of the Igiagig Village Council, Alexandra has been a driving force behind the community's efforts to generate its own energy from renewable resources. Joining Alexandra is Carl. Carl was raised in the rural villages of Kokkinok and Naknek in southwest Alaska. He graduated from the United States Merchant Marine Academy in New York with a Bachelor's of Science degree in marine engineering. Carl worked as an engineer at Navy destroyer and submarine design sites in Crystal City, Virginia for several years before returning to Alaska and obtaining his Master's of Science degree in environmental engineering at the University of Alaska. He worked in the environmental remediation industry for many years before moving with his wife and 2 children to Igiagig 10 years ago. Carl is the Igiagig Village Administrator, Igiagig Village Council Vice President, a commercial sockeye salmon fisherman, and a manufacturing business owner. Thanks to each of our presenters for making the time to join us today. With that, let's get started with our first presentation. Jim, you may proceed once your slides are up.
Okay, just checking you can hear me.
Yep, you sound good.
All right. So I'm Jim Reilly, as James had mentioned, and this is just a high-level introduction to microgrids, smart grids, energy resilience, and some of the hardware that supports it, and also how some of these terms are different from each other. Next slide, please. So yeah, just a quick agenda. This is sort of a high-level, oversimplified introduction into power distribution, power generation, microgrids, smart grids, and renewable generation, batteries. It tries to touch on all of that, which is typically probably 6 months to a year worth of coursework into about a half hour. So it is very high level. If there's any additional questions, feel free to reach out to me. I believe my contact information is at the end of this, and I'm happy to provide additional information. So what I'll step through today is just a high-level overview of the electric grid. What is a microgrid? What is a smart grid? Variable generation, batteries, and then there's an NREL, continuously optimized resilient energy like a microgrid design process, which is useful and provides a little bit more context. And it's a formally published document. Unlike this is largely like a discussion thing that we can drive the conversation today. Next slide, please. So just to align everybody's understanding on with some common terms. So distributed generation, there's a number of other terms that can be used there. Typically, it's any type of power producer that is connected at a lower voltage, and it is more distributed. Previously, the electric grid was more centralized generation, big power plants, and they were through transmission lines, they sent power out to the customers that way. But with the coming of renewable energy, and that's driving more distributed generation. A dispatchable generation source is any generation source that I oversimplify it by saying you can turn a knob and that generation source will go up or down. So it's something like a diesel generator or a battery or fossil fuels or hydropower in most scenarios. And those can be operated a couple of different ways. There's a graphic on the left that sort of shows how they're dispatched throughout the day as the load on the electric grid changes. Then variable generation are things like wind power, solar power, marine hydrokinetic. In some instances, hydropower is operated in a more variable sense, maybe on like seasonally. But typically it's more of a dispatchable source. If you turn a dial, it 100% will produce power when you need it to produce power. And then on the next two is reliability and resilience. A lot of folks focus on resilience, the ability of a system to adapt, withstand, and recover from a disruption. But reliability is just as important, if not more important. The whole point of reliability is trying to avoid the number of outages on a system, and electric utilities are experts at this and have pretty great reliability, somewhere typically in 99.9 something %. And then on the right, it just shows a quick example of like solar photovoltaic output. This is just an example, but that is, even though the sun looks like it comes up and you get higher production throughout the day, and then as it sets, it would go down right around that 5:30 on this graph. There are a lot of variations in that throughout the day, just as cloud cover and things like that pass over the generation, over the PV panels. So next slide, please. So this is just again a really high-level overview, just to provide some insight into the electric grid. So the electric grid is largely split up into transmission and distribution, and my personal example on the right in parentheses is that transmission is typically metal towers, and that's shown sort of in the middle of the screen here, I believe in blue for transmission lines. Power transmission is meant so that you reduce the amount of losses and you can transmit AC electric current over longer distances. Distribution is typically lower voltages, something like 12,470, 12.7 thousand volts, 22 kV, 34.5 kV, or 69 kV, in those ranges. And that varies when the distribution system was built and things like that. But typically they're something along the lines of these two, but it's definitely specific to each system. And like I was saying on the left, so this is sort of typically how the electric grid used to look. It was a generation station, power was stepped up to transmission lines, and it was sent over those large metal towers. Could be sent hundreds or thousands of miles from like southern Texas all the way up to northwest in Washington or something along those lines. And then once it gets to the location, they typically use a step down transformer, which changes the voltage from a high voltage to a low voltage and distributes it typically along wood poles is what you've seen, but there's a number of variations, metal and concrete poles as well. And that's how it usually gets to the consumer. And then there's another step down that occurs typically, and it goes from these 12.47 or 34.5 kV down to an actual usable voltage in our homes and things like that. So 120 volts, 240, or 480 are common voltages that you might have heard of before. Next slide, please. Okay, so to dive in a little bit, so microgrids, what is a microgrid? So this graphic I like to use because it shows sort of the scale of a microgrid that you can have within one example system. So there you can have a microgrid is a group of electrical loads like fans, lights, and anything that consumes electricity, and distributed energy resources, just a source of generation within a defined area. And the big thing that sort of is this is discussed internationally as well, is that the term for microgrid, this is a difference between the US and some other areas, but the US Department of Energy defines a microgrid as a system that can operate connected or disconnected from an electric grid. Some of the areas up in Alaska, I think those are typically considered isolated grids. They don't have the ability to connect to an electric grid, but that's sort of just nuances in definition. But they have a lot of the same challenges. Specifically, isolated grids, and folks up in that area are the experts in operating the area of microgrids that most other folks don't get to. Next slide, please. So microgrid operation modes, like I was sort of saying there, a microgrid can be operated in two major modes. It can either be operated in grid tied mode, and during that sort of operation, the generation and loads within the microgrid are usually used to try to help participate in some sort of energy market, whether it's using generation to shave the peak. So as your loads typically throughout the day, there might be some times where all of your loads are on at once and you have a peak, and that's typically what sets your highest electricity rate from the utility. So being able to use your generation to sort of shave that off can be a huge source of cost savings. Frequency regulation is actually trying to help manage and maintain balance across the electric grid. The electric grid's a big balancing act, and your generation can sort of participate in those markets to help balance the frequency of the regional system or even the larger interconnect, like the Western interconnect or the Eastern interconnect. Demand response, again, you can serve as support to your local electric utility by turning off lights and other heavy loads, which could then help reduce your utility rate, or the utility may actually pay you to participate in this demand response. And then isolated mode or islanded mode is, again, that's the area where up in Alaska, they're sort of experts in operating in islanded mode. So you're operating with no connection to the electric grid. You've opened the circuit breakers and the switches that connect you to the grid, and you're operating sort of as a standalone power grid. There's two typical ways that a microgrid transitions into this space. It's like load isolation, which is planned, and that can be a response to a demand response signal from your utility. And then the second is emergency power. So if the power goes offline and you weren't planning for it, how does your system respond to that? And I'll step through that in the next two slides a little bit. On the right, this is typically a moving graphic that shows how generation has to be sort of synchronized and operating perfectly coordinated to be connected on the grid. So when you're switching back and forth between grid tied operation and islanded operation, there needs to be a lot of coordination there to make sure that you're actually coupling with each other. And there is a link down at the bottom that has that graphic in it as well, but it just shows that they're out of sync with each other, and then little by little one generator catches up, and then they synchronize, and then they connect to each other. So next slide, please. So this slide dives into in a little bit more detail in a planned microgrid transition. So again, this can be an example where a utility asks you to respond to a demand response signal. They have not enough generation on their system and too much load, and they want you as a customer to, your microgrid as a customer, to drop off. So this is planned, and you can actually sort of coordinate this whole thing. So what happens up in the top left, steps 1 through 7, it states that you bring all of your microgrid generation online and get ready to serve all of your own loads. Just like that graphic up top in the last slide, you synchronize your generation storage with the electric grid's generation. Then you try to make it so that your generation is meeting your own load, and then there's no power going in or out to the utility. And then once you sort of have zero power going across that line to your utility, then you would open that switch and you're now operating as an isolated grid. And all of that can be done sort of manually or automated, and I'll get into that a little bit later when we start talking about smart grid in that space. And then once you hit that point, you're sort of operating as your own islanded or isolated grid. And to get back to the other way, it's sort of the same steps, 1 through 7, but just the inverse. So it's step 7 through 1, largely just reversing the process. Next slide, please. And now an unplanned transition. This is if a tree falls and takes out the power outside of your installation or something larger than that, a large storm. So you weren't able to bring all of your generation online, have it coordinate with your loads, and then seamlessly transition to isolated or island mode. In an unplanned system, everything's offline. That fault occurs if you're not configured with large batteries and spinning generation. If everything is offline, your microgrid will go offline. So that's definitely a major consideration when pursuing microgrids in this space. Typically, what would happen is the protection system, circuit breakers and reclosers and things like that, they will trip the system offline to make sure everyone is safe, no fires are started, no one gets electrocuted, things along those lines, and the equipment doesn't get damaged. So everything will shut off. There'll be a short-term or long-term power outage. So then in this short gap on the bottom right graphic here, so there's going to be a short little outage there, and all of those steps 1 through 8 occur there. So depending on whether the system is manually operated or automated, either the system will start bringing itself online by bringing up generation and starting to shed or turn off some loads so that you have enough generation to meet your loads. And then you'll actually start bringing the system back online using your own personal generation. If it's a manual thing, a lot of electrical linemen and technicians would be dispatched, not a lot, but a number of electric linemen and technicians would be dispatched, open a number of switches to make sure that the area you want to operate as an island is isolated. They'll be dispatched to start bringing the generation online, also opening switches to disconnect some loads so that you have enough generation to meet the loads that you need to operate during this outage, this islanded or isolated operation. And so depending on if the system is automated or manually operated, where I say all of that happens here, that could be 30 seconds to a minute. So typically, this is a good example of a standby generator in a building. This could take between like 10 to 30 seconds, or if it's a large system, it could take a couple of minutes to be brought online in an automated fashion. If it's manually operated, it takes folks a long time to drive out in trucks and open switches and make sure that everything's safe before bringing generation online. It could be an hour to 3 hours or more, depending on the severity of the issue. So yeah, just trying to explain the two different ways that a microgrid can transition between here on slide 7 and slide 8, and also just the impact on the amount of time you would experience an outage. Next slide, please. So this is, again, sort of my personal way of thinking through what is a microgrid. So a microgrid is, again, just sources of electricity generation, energy storage like batteries or pump storage, hydropower, loads, which is lights, heaters, fans, anything that consumes electricity in your building, power and transmission and distribution lines, and then switching and protection devices. On the right, that shows an air brake switch, which isn't typically supposed to be opened, and it shouldn't have an arc, that bright white line in there. And then on the bottom right is a lineman manually opening a fused cutout, a fuse in the bottom portion here, and then power voltage correction, so voltage regulators and capacitors. In this conversation, I won't dive too far into this, but one of the more detailed electrical characteristics is reactive power, and people like to talk about how you need real and reactive power to serve all of your loads, because some loads, quote unquote, consume reactive power. So electrical engineers always like to show the graphic of the beer, because a lot of folks like beer, and it is a good analogy that you need a good balance between actual like liquid beer and the foam on top. So power or voltage correction, typically the voltage regulator and capacitors support the management of the beer in the electric grid. So to oversimplify this slide, I like to state that everything around a microgrid is the electron carrying portion, the electricity aspects of your system. So next slide, please. So what is a smart grid? And this is sort of just to introduce what the differences there are. So a smart grid is interconnected generation and loads with remote monitoring and controls capabilities. So on the bottom graphic, I show what's sort of just the monitoring and controls aspects of this. And it's a number of controls and like number of relays that are deployed out in the system to actually control all of the switches and generation that we were talking about before. It's fiber optic and wireless communications to send signals to control that your generation and loads out in the field. And then it's this central server that's sort of the brain behind all of the everything that's actually operating your intelligent grid or your smart grid. So next slide, please. And these are, again, sort of my examples of what components of a smart grid are. So there's current transformers and potential transformers. Those basically just read the power flow and the voltage of your system that's sort of the monitoring side. It gives you the ability to read the status of your electric grid. The relays are a point that the CTs and the PTs communicate with. So that's sort of the hardware at each individual node. Then there's communication that the relay communicates over fiber optic or radio, wireless, or even line signals. Just how that signal from your solar PV or your load or your circuit breaker at your substation, how that signal gets to some other point. There's a number of softwares that are out there, and then getting over onto the right side, it's sort of stepping through like these are how you visualize the data, how do you manage the data, how do you actually make informed decisions based on the data you're receiving from the stuff on the left. And on the bottom right is just an example that I just pulled off of Google somewhere, but it shows what this like visual interface might look like, and you can see that there's a steam turbine generator and it's showing output of the system, and then on the right side of this graphic, it's showing the substation and the status of power flowing across circuit breakers into individual feeders within this system. And then on the left side, I always like to show this example. This is a picture I took a couple of years ago that shows analog relays, and these are sort of related to the CTs and PTs up there. So these read things like current and voltage and frequency of your system, and they were designed that if there was an issue, they would actually serve to trip your circuit breaker, just like with the one on a home, to make sure the system is protected. So if any of those analog relays, if they go out of bounds, what's considered safe, the system would trip offline. The new digital relays on the bottom can do what all of those analog relays did on the top and much, much more. So there's a lot more functions that are added into there, but with that comes additional cost and complexity as well. So next slide, please. So this is a fun graphic. Normally the center transmission tower is playing jump rope. I don't think that ever actually happens in the real world, but it's just usually serves to wake people up halfway through a slide deck. And then, so this is again another way that I like to talk about microgrids and smart grids. So you can have a microgrid that's operated largely in a basic sense, so it's more manual. So like I said before, you're dispatching linemen and technicians to go out and open switches and things like that. And It's heavily coordinated, and the manpower behind it is heavily coordinated. Then you can have sort of an automated process. Maybe the generation is brought online based on what linemen are reporting into a system, and after opening and visually securing that your islanded grid is in fact islanded, the generation will sort of bring the system online itself, or maybe there's some aspect of load shedding that is automated, but other portions are manually operated. And then on the far right, and this is especially happening as we get further into the renewable, the realization of renewables in microgrids and inverters, which is how renewables connect to the grid typically. A lot of that is sort of power electronics and a lot of computers, the way that it's connecting into the grid. So the ability to bring systems online in an automated fashion, a more advanced fashion, is becoming easier, more common, and a little bit cheaper. But there is a lot of complicated coordination that needs to go on there, and regular software updates and things like that. So yeah, this is just trying to make the point that a microgrid can be extremely basic and manually turning on a generator and opening switches to isolate your grid, or it can be completely automated with batteries operating a system, and if there's an outage, the batteries coordinate with a central controller to open switches, and there's almost no human intervention that's even needed, or it can just check with a human to see if it's okay if we do this and move forward, is everything safe? But there's a wide variety there, whether something is like manually operated or automated. Next slide, please. So this is again just sort of to reinforce that the differentiation there. So a smart microgrid is sort of two main layers is how we think about it. And I'm an electrical engineer. My expertise typically lies in the electricity side, the wires side. And I typically coordinate really closely, and I'm getting better at the control side as well. But on the bottom right, I like to visualize a smart microgrid as two main layers that are heavily coordinated with each other. So around the outer edge, you have all generation, fuel cells, electrolyzers, wind, biomass, hybrids, batteries, solar, things like that, putting power into the wires that are going around and maintaining a balanced system. And then in the middle, there's a communication layer that's making sure all of that stuff is coordinated and you're maintaining a balanced and safe system. And as the smarter a microgrid gets, it also enables additional markets that the system can participate in. So again, your utility may pay you to provide some of these services to them if you're a large enough customer. And so there's an economic analysis that can be seen there on this incremental cost in hardware enables you to have an extremely smart microgrid, and it also enables you to have this new source of potential revenue that your system could save and help to pay off the overall capital cost of the system. Next slide, please. So variable generation in a microgrid, these are things again like wind and solar. There's a lot of benefits to having wind and solar in the grid. My background is typically working with the Department of Defense, and one of the biggest risks to the Department of Defense is the shipping of fuel. So bringing diesel fuel to a site to power that site is a risk, whether it's from an actual tactical advantage or if it's just from a threat perspective of like storms and weather. I think I was working with someone up in Greenland where they bring in diesel once a year up there, and this was a very, very big system, but that's the only time they can ever get a tanker up there to actually refill the diesel storage. So they were asking if we could try to investigate wind, solar, or geothermal or any other potential resource to give them more of a diverse set of resources so they don't have to rely on that shipment of diesel fuel. So it's not necessarily a free source of energy, but once you install solar and wind, if the resource is adequate in that area, it's largely, you're just relying on the earth to provide your electricity versus trying to ship fossil fuels around, which has a number of risks along with them. But to dive into this slide a little bit, the way that this gets a little bit deeper, but the way that you consider variable renewables when in contrast to something like a diesel generator, is slightly different. So you can see on the bottom left, variable renewables, wind and solar, fall very much to just what their name states. They're variable. Daily, the sun goes up and comes down, so your solar PV may only be producing during the day, and then a cloud may come across, and the production output from that may come out, or may be reduced or shut off. And the same thing with wind. As the wind increases, you start producing more power. If it gets too high, the wind turbine will actually shut down, and if it's too low, there's not enough wind to turn the turbine. So when you're considering them, typically it's thought about in two different aspects. So there's a planning aspect, understanding how much generation you need, compared to like diesel generation, energy storage, and renewables, and also the fuel that you need to store for your diesel generation. That's sort of on the planning side. If you have solar PV and wind sort of offsetting some of that diesel fuel, there's an inherent benefit that you don't need to store as much diesel generation on site, or don't have to have it shipped in as frequently, different things along those lines. But yeah, so the challenge is that wind and solar are not like a capacity resource. If you have a 500 kilowatt diesel generator, you're going to typically get that 500 kilowatts if you need it. But if you have a 500 kilowatt solar PV array, it may not always be there. That's why as energy storage is getting cheaper and cheaper, it helps to shore up that power that you could be getting from wind and solar to make it so that it's always there. And that doesn't devalue wind and solar. It just is a consideration that needs to be thought of as the system is going forward. And in operation, this is sort of the example on the bottom left. Wind and solar are varying, but also load is heavily varying. So you need energy storage, or diesel or fossil or natural gas generation, or hydropower, some other source that is more dispatchable to sort of complement the wind and solar and manage those variations throughout the day. And our load varies as well, so it's just another consideration of variation that you need to bring into the system. So I've typically always liked to think about power system planning, and this is how utilities think about it, in two steps of planning and actual day-to-day operation of the system. Next slide, please. And then here's sort of a graphic of, it's sort of a non-technical overview, so any electrical engineers that are on the line, I apologize, but so this is my explanation of a battery. So when you're having conversations about a battery at your site, there's two main numbers that you would need to think about. So the capacity of a battery is similar to the peak output of a diesel generator. So a diesel generator is sized, for example, to 500 kilowatts. A battery would typically also have that capacity value of in kilowatts, but that sort of tells you the most amount of power that the battery can put out through its power inverter at any specific time. To translate, the second aspect of a battery is sort of like the fuel tank for that diesel generator. Everyone talks about fuel and diesel in terms of gallons, but the fuel for batteries is typically spoken about in watt hours. It's the energy side. So if you look on the right side, these barrels sort of represent a 2 megawatt production into that large arrow, and you could put out 2 megawatts and that would be about a half hour. On the right side, these two barrels, you could only put out 1 megawatt, but it could run for 2 hours. So it's a 1 megawatt, 2 megawatt hour battery. And then the power inverter that I mentioned, that sort of determines the capacity of the battery. So a battery outputs at DC, just like in cars and our phone and things like that. And then to connect to the loads that we typically have in all of our systems, there's a power inverter that converts it to AC. So that's sort of the capacity limiter of the system, is typically the inverter. On the bottom right is just an example that shows some of the ways that a battery can be used to support your local utility or regional energy markets, but also how it would typically be dispatched and operated in an isolated or an islanded grid as well. When there's a ton of solar PV and wind, you're sort of storing all of that energy storage, and then as those may decrease, you use the energy storage to shift the production off to the edges of the day. or when there's not enough generation available. Next slide, please. This is just a graphic that shows is an overview of the NREL, some of the NREL sites. There's a number of wind turbines that are up at our Flatirons campus, and we sort of use all of these systems and actually just had to use it in the last month to operate as an isolated grid because of an outage that occurred that was serving our Flatirons campus. So they configured it to run, so this is the graphic up in the top left. There's the 1 megawatt solar PV array. The batteries are not actually shown on here, but there are 1 megawatt hour batteries. And then the GE Alstom 1.5 megawatt turbine on the far right. All of those were connected and actually operated as a microgrid, which was sort of a forced research scenario, but it was a successful research scenario, and we're working on documenting that. But it's a cool example of an isolated grid or a microgrid. But this is also largely something that wind and isolated grids is largely an expertise up in Alaska and island nations and so various areas. So it's but we got to do some pretty cool tests and show that wind can provide more than just energy to a system. How can wind support sort of inertia of your system, or that beer example, the reactive power further up. And then next slide, please. So this is just an NREL microgrid design process that we're currently working through, and it's like always being updated and revised based on new information, but it's sort of a 5-step process: high-level scoping and planning. Who do you need on your project team? What's some background information? What are your most important loads and like buildings and things like that? What are some of your risks? Are you in California and wildfire and earthquakes are some of your highest risks? Or are you in the Gulf of Mexico and hurricanes are your highest risk? Or is it in the mountains of Colorado or up in the Northeast and winter storms might take out power? What are the goals of your system? Do you want to participate in markets? And what are some of your expected performance requirements? And that's largely a conversation that would happen with the designer of the system and you, the end user, the customer. What are your needs and what are your requirements? Is a short outage okay with your system, or do you need sort of seamless power with it never going offline? That second scenario, seamless power, is more expensive. Just understanding that there's cost trade-offs for any decision that's made in this process. Step 2 is data collection, just getting all the information you need to perform analysis in support of step 1. Step 3 is conceptual design. You start coming up with what, at a high level, what is your system going to look like? How much is it going to cost? What sort of communications do you need to meet all of the requirements that are defined in step 1? And this is sort of a cyclical process where you go back and may have to iterate a number of times before you get to the end system that you actually want. And then step 4 and step 5 are largely Department of Defense and federal agency requirements, but you go into the request for proposals and sort of the open solicitation side. At the end of step 5 is actual engineering design of the system, construction and like testing of your system, running a number of studies to make sure that everything is safe, and if anything fails, everyone will be safe and no hardware will be damaged. And that occurs between those two, between commissioning and performance testing. And then the last one, which is sort of the side that the federal government is working on and was sort of a lessons learned in the last few years around microgrids and smart grids, is operations and maintenance. A standby generator, typically you put it out there, do some routine maintenance on it with a diesel mechanic, and it's fairly reliable. A control system for a microgrid and some of those other larger aspects require constant maintenance. On cell phones and computers, we get constant updates, and a control system should be getting relatively frequent updates and maintenance on that system to make sure that it's operating safely and will work when you expect it to work. I think that's the last slide I was going to step through. So James, was that enough time, or should I step through those couple of examples on slide 22?
Jim, I think that's great. I think let's just proceed. We're getting some good questions, so let's try to make sure we have time for questions at the end. Thanks, Jim. Excellent presentation. Complicated topic. I appreciate your skill in kind of bringing it down to an understandable level for us laymen on the phone or on the call. With that, let's move into a couple case studies. First one here, Kelsey is going to talk to us about a village relocation and desire to implement microgrid as part of that process. So Kelsey, go ahead.
Thanks, James. Hi, I'm Kelsey Moldanke. I'm Senior Planner for the Quinault Indian Nation. Next. So I'm going to talk about our project overall, give you a background of our relocation project. I'll talk about the effects of climate change on the Quinault Nation. I'll talk about our overall energy strategy, get into our microgrid, and then talk about next steps. Next. The Quinault Indian Nation, the reservation is on the Olympic Peninsula of Washington. You can see there on the left of the screen. The village of Taholah is at the mouth of the Quinault River. Taholah is about 2.5 hours from Seattle and 3 hours from Portland. Next. So Taholah is kind of naturally split into two areas. You have the lower village, which is down at the mouth of the river, down right at the ocean, at the beach, very low lying, and basically at sea level. And the upper village, which is shown there in yellow, it ranges from 85 feet elevation at administration building up to 165 feet of elevation. You can see that we have many important uses in the lower village, such as the mercantile, which is the one store and one place to buy gas, the community center, school facilities, and the museum. So kind of the cultural memory of the village is in the lower village. Next. Taholah is subject to dual threats of sea level rise and the tsunami from a 9.0 earthquake. As mentioned, Taholah is very low lying, so any effects from sea level rise from a foot or two or more would be very deleterious on the village. That's sort of a drip, drip, drip problem, literally, that would occur over time. The tsunami from the 9.0 earthquake would be much more destructive and happen all at once. A tsunami would likely be triggered by the Cascadia subduction zone, which is offshore. It has similar tectonics to those that caused the Indonesian tsunami in 2004. According to geological records, major quakes and tsunami occur every 300 to 500 years. We're 320 years into that cycle. The ground would shake and sink 4 to 6 feet. Therefore, roads would likely be damaged. So it's unlikely people would be able to drive out of the village. The water table is high, and the village is built on the old estuary, so it's fill. So geologists tell us that during the quake there may be water shooting out of the ground. So we do drills annually, but they're always during the day, and usually it's decent weather. And even then people don't necessarily make it up the hill in 20 minutes. So in the case of an earthquake that happens at night in bad weather, your house may be damaged. You have to gather up a bunch of your kids and get up the hill. It's unlikely that everybody in the lower village would survive. And even if all the residents did, they would have lost all their possessions, and then we'd have a large homeless population for months because the houses would all be gone. So therefore, because of sea level rise and tsunami, the Quinault decided that a move to higher ground is necessary. Next. As you can see in the photo, the village is not much higher than sea level. That's a picture taken in a minor storm from the seawall. The seawall does not extend to the full length of the village, so sea level rise would be deleterious for the village. In terms of resources at risk due to climate change, clams would be harmed by ocean acidification. Salmon are already being affected by warmer waters in the ocean and the river. The river is subject to lower, warmer flows, especially in the summer, because of the loss of glaciers at the headwaters of the river in Olympic National Park. The reservation is mostly forest land. Climate change could increase fire danger and increase pests. Timber, salmon, and clams are major economic drivers for the Quinault, and any adverse effects on them would have adverse effects on tribal members. Clams and salmon are of great cultural importance, so if these resources disappear, the culture would suffer a great loss. Because of the QIN's acknowledgement of climate change, there is a desire to pursue renewable energy strategies as well as relocate up the hill. Of course, the most important resource is the Quinault people themselves. Next. So here you can see the recession of the Anderson Glacier at the headwaters of the Quinault River in the Olympic National Park over the last 100 years to the condition it is now on the left, which is, for all intents and purposes, gone. It's now a lake. Next. This shows the likely tsunami inundation in the lower village from a 9.0 earthquake. This was modeled by the Washington Department of Natural Resources. As you can see, the entire lower village would be wiped out, as well as senior program, Head Start, the whole of school, and some of the other programs I talked about earlier. Next. The area in pink is the lower village, and that shows 40 to 50 feet of depth of water from the tsunami. That's much deeper than any building in the lower village. And then you can see the relocation there in the southeast corner. So at least thankfully, people would not have to move far, and there is at least some infrastructure in the area. As mentioned, the Quinault decided to move because they realized the threats from sea level rise and tsunami, and have and came up with the Tahola Village Relocation Master Plan, which is what I came on board with the nation to write the plan. Next. We're also threatened by landslides on the reservation. As you can see in the lower left-hand corner, that's the one paved road that serves the village. And that road goes through the tsunami zone. And you can see on the right is also subject to landslides. We've had 2 major landslides close the road for a couple days in the last 2 years. Thankfully, it didn't take out the power infrastructure, which you can see in the picture there on the right. So both the road and the power line, that's the only power line that serves the village, go through the tsunami zone and the areas where there's landslides. We've also identified a future probable landslide that could take out both the highway and the power infrastructure that's shown in the gray there. The bluffs are being eaten away and sliding, and it's getting very close to State Route 109. That's only a couple miles south of the village, maybe a mile, and so that would even cut us off from the backup escape route, which is a network of dirt roads, gravel roads that can connect out to other roads. Next. As part of the master plan, we of course solicited community input. We did community surveys, we had community dinners and raffles, we went door to door, we had online surveys, but really the best information we got came from just talking to people. I mean, there was a staff of 3 of us dedicated to this project that came aboard specifically for this project. And we would just go out and talk to people, and that's where we would hear a lot of their concerns and a lot of their ideas. Next. So a lot of the community input centered on elders, the family, knowing each other, trusting each other, helping each other, the kids, culture, and everybody matters or nobody matters. Next. In our village, there are about 175 homes and 650 people. There's a housing crisis on the reservation in that there are a lot of people that want to move back to the reservation, and there's no place for them to move quite yet. And so we have a waiting list for both home ownership and rentals. There's about 175,000 square feet of community buildings that need to be relocated and expanded. And there's an 80,000 square foot school. That's a state-run school district. So the nation doesn't necessarily control when that can move up. Next. The master plan, we tried to incorporate traditional plants. You can see one of the elders picking Indian tea, and then there's camas. And we wanted to integrate those into some of the wetland areas and landscaping. We worked with Quinault artist Marvin Oliver on art integration in the new building that we're just about done with, the Generations building that will have the senior program and early childhood education. So beyond incorporating culture into the built environment, some of our local artists were able to have designs made in new media that they hadn't before, like metal, and were able to meet local fabricators. Hopefully this will expand the market for their art and bring them more visibility, ultimately providing them economic benefit. Next. Just briefly, here is a concept for the village centered around the school with various neighborhoods with mixed densities, parks, and community building. Next. We worked with Washington State University on the quote-unquote Quinault House. This isn't a specific house design, but it is guidelines and suggestions for both individuals and the nation for residential and community buildings. It was meant to be energy efficient and climate appropriate. We get 90 inches of rain on the reservation. We're right on the coast, so we get a lot of salt air and high winds. So building integrity is of great import. We reached out to Department of Indian Energy, and they provided us with some technical assistance with NREL. They reviewed the Quinault House report that Washington State Extension prepared for us, and we incorporated their comments. Next. As mentioned, the energy infrastructure that serves Taholah is very vulnerable to natural disaster. So we need a way for folks to safely shelter in place for months, up to a year, 2 years. In the case of the big one, the Public Utility District thinks that they may have to go 40 miles inland and rebuild the entire system. And since Taholah is at the end of that system, they'll be the last to get power restored. So how can we have people safely shelter in place for months? So we looked at doing an energy park in the upper village that would consist of biomass and 1 megawatt solar array. Next. Our energy strategy is overall based on the Blue Lake Rancheria, in that there's a variety of power sources. We have a lot of slash on the reservation left over from the timber operations that otherwise just gets burned on site. So we thought, why can't we bring that flash to Tahoe and grind it into hog fuel and then use it in a biomass burner to heat water, which then powers heating in community buildings. It's very wet on the reservation. Again, the 90 inches of rain. So that was initially a bit of a problem, but we found a system based in Burns, Oregon that can take the wet wood. We have a biomass building with architectural plans complete and engineering complete. Now it's just a matter of funding to get that online and then connect it to the administration building, the clinic, and the generations building to provide some heat. Next. As you can see in the orange line, shows kind of where the pipes would go from the biomass facility down the hill to the generations, the clinic, and the admin building. It's across the street from the school. It's been designed so that you can expand it so it could serve the school, it could serve a recreation building, it could serve museum, whatever buildings we come up with in the future in the Upper Village. Next. We've been concentrating recently on solar energy. We have designs completed for 100 kilowatt arrays with battery backup that are combined with a generator for the generations building, and then another system for a new Head Start building we want to build in the other village of Queets to the north. We're looking at a 1 megawatt microgrid array for providing resilient power for a long outage due to disaster. That would, of course, have energy generation, storage, and distribution. Right now, our buildings are backed up by diesel, and if the roads get cut off, the question is, how much diesel can we have in the village? How long will that last? So net metering is good, which would happen with both the microgrid and the 100 kilowatt arrays, but that's not the driving force for this. It's just survival. So net metering is good, but survival is imperative. Next. So we have a microgrid study complete, as well as the plans for that 100 kilowatt arrays. So right now we're in phase one, as laid out by the microgrid study. We have a concept development. It identified potential partnerships and funding assessments. In the future, we will have to look at utility infrastructure upgrade, see how much those will cost, and do microgrid load study analyses. And then eventually we will have to have design complete, done, and contracting and building and hooking up the system. Next. Again, our system is designed for resilience using large battery systems with arrays. It's not necessarily for energy cost savings. That is just a benefit. It'll be a great benefit, but again, it's resilience. It's keeping people alive and in good condition that we're most concerned about. Next. So you can see there the estimated annual energy use. It wasn't really sustainable to keep all the buildings in the new village powered for 2-year duration. So that would take a much larger system, somewhere in the vicinity of maybe a 5 megawatt system. So the aims are to keep as much power on as possible, but not serve every house and every need. Next. According to the study that we have had done by using programmable inverters and central controllers, the system is technically feasible and will allow us to island during disaster situations. Next. During our project kickoff workshop, it was also highlighted that there are potential for training opportunities and workforce development with QIN tribal members and our TARO program, and that this workshop and this workforce development would also raise awareness about the project within the tribe, on the reservation, and in the North Beach area. Next. The study indicated that in 10 years, the cost for 1 megawatt will probably be $1.4 to $2.5 million. So where do we get funding for the project? We would look at USDA. We'd look at the Department of Energy Infrastructure Deployment on Tribal Lands grant, both for the microgrid and the smaller 100 kilowatt arrays. To Tribal Solar Accelerator Fund, the State of Washington Clean Energy Fund. We could work tax equity investment, that would be great, or maybe hire design build operation. Next. Right now, we don't have a road up to the site. We have a road about halfway to the site of the energy park, and we don't have piping in. And I think those sort of have to go together so that you can't really put the piping in and then build the road on top of it, because then you might be jeopardizing the integrity of those pipes. A lack of electrical infrastructure is probably even more important. Number one, the infrastructure and the existing housing that's up on the hill is 45 years old in parts and 25 years old in parts, and would have to be upgraded. It wasn't designed for an entire new village. It was designed for 50 homes. So that would need to be upgraded. And then there's a lack of infrastructure to connect to the rest of the grid. You saw the power line that we have. The nearest substation is 10 miles away. So I think that 10-mile stretch would probably need significant upgrade. I believe the Public Utility District has indicated that. So hooking up the 1 megawatt system isn't necessarily straightforward. And then Clean Energy Fund Grid Modernization Grant is the most likely source of a lot of money, so we'd have to rely on coordination with the Public Utility District and hope that they are behind the project also. Next. We've worked with federal agencies to get as far as we have. We got technical assistance from the Department of Energy Office of Indian Energy, both for the Quinault House and then doing very high level advising on the microgrid at the very earliest stage. We have a grant from the BIA to design the 100 kilowatt arrays and look at the microgrid. And we've worked with the Bonneville Environmental Foundation. They gave us money to do a study before we got the money from the Bureau of Indian Affairs to look at renewable power in the village. Next. So what do we do next? We'll have to do a load study. We'll have to work with the PUD on transformer upgrades, and then come up with actual development plans for the microgrid. Probably would help to have some more of the buildings built up there so that we have a better idea of the necessary loads also. We've only got one building done, but more are on the way. Where do we go next in terms of the relocation? More grant writing, fundraising. We need strategies to help people relocate, especially if they have mortgages. We need something to incentivize people to move up the hill and maybe potentially have another mortgage. We need more architecture and engineering plans, both for buildings and for the microgrid. We've got one building down in terms of getting built, so many to go. Thankfully, at least we have plans for the kilowatt arrays. Moratorium in the lower village, once there's a place for people to go. More studies, new staff. We'd have to consider new parks maintenance, or we don't really have anybody on the reservation trained in solar power operations. We would need somebody trained in the case of the microgrid, obviously. So that would take new employees. We want to keep looking at alternative energy projects, build the arrays, and then relocate parts of Queets, the other village. Next. Siokul, thank you.
Thanks, Kelsey. what a challenging undertaking, but also a great opportunity to kind of start fresh on the electrical infrastructure side, or start fresh might not be right, but start from little rather than trying to retrofit a bunch of stuff. Our next presentation, another case study from the native village of Igiagig. Somewhat similar scenario, but a very interesting case study as well. So with that, please, Alexandra and Carl, proceed.
Guyana, can you hear me okay, James?
Yeah, you sound good.
Okay, I'll kick it off. Ababi Kaigunga, Ifeyakakamiungunga. I belong to the place where Lake Iliamna, which is Alaska's largest lake, is flows into the Kvichak River, which then flows into Bristol Bay, which is hosts the last largest wild sockeye salmon run left on Earth. So we're pretty proud of that. The title of our presentation is called Igiagig Microgrid, the Why and How. I think it's pretty cute because in Igiagig, that implies micro. Everything about us is tiny. We are a little nation of 70 people, and the Igiagig tribal government is a federally recognized tribe that also is the only local governing agency and owns and operates almost anything that we do here, including the electric company. Currently I'm the president, and co-presenting with me today is our vice president, Carl Hill. Also, he's the tech man. I'm just here to give the broad overview. So next slide, please. Next slide. Okay, so basically the why. There's a little graphic of Igiagig located there in Southwest Alaska. We're pretty proud that for 9,000 years, or as we talk about it, time immemorial, our people have lived here in this same area and lived sustainably. And it wasn't until all of these recent land and settlement actions have resulted in a situation where we're extremely dependent on diesel, to the point where we have seen the fluctuating price of fuel, and it affects all levels of village operation. And then we are reliant on something called the Power Cost Equalization Program, which helps to equalize the cost of power in our remote communities. But that's something that's always, it seems, perpetually on the chopping block when it comes to legislative priorities. And so I always think about our resilience or our situation currently as it is dependent on diesel as highly dependent on what's happening at other levels of governance. And so we would like to insulate ourselves from that. We can only make our ends meet while these systems are in place. And you change one factor and it will affect everything. So 20 years ago, this writing was on the wall, and our leadership met and said, in 2025, we want to be diesel off. We want to pursue alternative energy, not only because it will be best for our people, but environmentally and culturally, it aligns with our values to have a low carbon footprint. When I talk about being in a landscape for 9,000 years and having no visual evidence of that, it's pretty remarkable. So we've really been on this path towards sustainability and self-determination and determining our own path forward. And so it really came from our own people even before the crisis. 20 years before the crisis the state of Alaska is in now. The next slide, please. So roughly, it's $250,000 to run our little electric company to serve our 70 people every year, and fuel is nearly 60% of that. So we're not saying that integrating alternative energy is going to hopefully, ideally, reduce the size of that pie, But even if it doesn't reduce the size, then maybe it can be reallocated. We don't mind if, for instance, the fuel slice gets reduced to 10% and that the cost is still the same, but say we have another job opportunity or a full-time maintenance worker or whatever you have it for serving this alternative energy, and then the payroll increases. So we have always taken this approach that even if at the very minimum we're not reducing the cost of power with whatever we do, whatever we endeavor, then if we are employing our own and not burning carbon, then we will be achieving our goals still, even if we're still paying the same amount. And so having that mentality is really important, and I make it a founding factor in what we're presenting today, because every time our village has been faced with an opportunity or a challenge, we have asked ourselves, well, what do we have to lose? And if we don't have to lose anything, then we can move forward. And so it set a pretty high bar, in especially thinking about that cost of fuel that you see. And in this slide, you'll see our fuel plane flying in, which is oversized for the size of our runway, and it's flying over the RISGen, which we're presenting on today, which is our hydrokinetic power. To me, it showed the phasing out, hopefully of our operations. Flying fuel in is very dangerous. Our runway is not equipped for it. Our equipment for receiving it is aging. Our bulk fuel farm, which holds 114,000 gallons, is situated at the headwaters of the world's largest salmon run. So we are feeling all of these things all hit close to home. On top of that, we're paying almost $1 a kilowatt hour. And if some of these programs that I just mentioned, like power cost equalization, were to go away, our residents would have a hard time affording to live in our community. And we're not unique. We're one of 250 microgrid communities in Alaska. Next slide, please. Next slide, Monica. Okay, so the how we came to this point. I talked about the 20 years of comprehensive strategic planning as a community. I sure appreciated that presentation from Quinault. Planning is everything when it comes to moving a project forward. I really feel like. So it came from that. We had this locally driven strategic planning process where we identified the people, consensus-based decision making. Alternative energy is the goal, and we want to transition from diesel by 2025. That was the goal, and there was no path forward. It was just stated. And the fact that it was stated and reevaluated over the 20 years, even before we began a hydrokinetic path, that was simply all our community needed was a target, and we began moving towards that. So we started testing wind, solar, and hydro options. We felt like we didn't want to put all of our eggs in one basket, and we weren't sure, what was going to work in the long term. So we started testing everything. We became a literal plug-and-play community, and I distinctly recall being up in Fairbanks at the National Renewable Energy Lab there, or maybe it's just some energy lab. But either way, I was thinking to myself, they have this entire lab of these generators and inputting all of these renewable options, and they're running this generator and just to simulate a village. And I thought, why can't we bring those resources to a real village and actually simulate it in real life? And that's what we became. So it took a lot. It has taken a lot, and we're going to share some of that journey. So the power plant needed to be upgraded so that we had the switchgear and capabilities to integrate, to even begin thinking about integrating renewables. So that, when you're talking about rural projects in Alaska, that had a $1.5 million price tag. So these are no small tasks. Then we opened up the Quinault River test site, the profiling and permitting. That took nearly $1 million just to become a test site and say, go ahead and test your devices here. Because the funding is so limited and it goes with the flavor of the day, whatever's out there, because of our fish population, our unique situation of the Quinault River is a very crystal clear river. At the mouth of it, it usually doesn't freeze because of the power. So we have, because of the power of the river current. So we have a real opportunity here, and we always felt like if it can happen in Igiugig, it can happen anywhere in the world. So because it's so geographically challenging to get here, as you'll see later in the presentation. So we let the hydro companies begin for them, compete for themselves, and let the state vet them who would be the best for testing their emerging technologies. Then we selected one company after watching everything unfold to move forward in hydrokinetic power specifically. And this presentation is focused on our hydrokinetic power efforts, but our alternative energy really started with looking at our wind potential. And that's another presentation for another day. So I don't want anybody listening in to think that we went about it just focused on our water. We really looked at everything, and we have gone down several paths, but the one that is most promising to date has been the hydrokinetic power potential. And we have been working with Ocean Renewable Power Company, and we would like to play a short video so that you have a very clear idea of our community and what this source of energy looks like. So if you'll bear with me, we have about 3 minutes here. Thank you. James, is it just me or is there no audio?
Yeah, sorry. Yeah, there's no audio right now, and I'm not sure why. I was hoping it was just on my end.
Okay, no problem.
I think luckily there is the link there in your slide deck, so at least people will be able to play this again on their own, because it looks like it's a great video, and the audio certainly would help complete the picture.
Well, definitely. So I can just narrate as we go. So we are a salmon-based society. We have a lot in common with what I saw with the Quinault Nation. And we have always focused on emerging leaders, involving youth in our decision-making, and even forward. Speaking now is how we appreciated that Ocean Renewable Power Company didn't come and say this could be the solution. They actually met with our engineers. Everything you see here on all these equipment, except for the RivGen, are all locally based. So these are owned by the tribe, and this RivGen has been tailored to being able to be deployed. That's a commercial fishing device, commercial fishing vessel, which everyone has because of the fisheries we have available. So everything is that this device has required to be installed, the anchors, the actual device itself has been done with local equipment. And there you see it spinning. It actually sinks to the river bed, and so it can be raised. And we have a buried line distribution system, so they're pointing out that it comes right to shore, and then it plugs right into the grid. and these are just aerials of the village. So we have a buried line distribution system, and Carl is going to talk about the next step, which beyond the RivGen, we have been funded an additional RivGen device. So with 2 devices, we can actually go diesels off, and we will have a battery energy storage system, and that's where we're headed. We have had one grant with Department of Energy Water Power, and then the second one with Indian Energy, and together we would be able to go diesels off. And I think we can end the video, the silent video, and let Carl take it from there to talk about the specifics in that.
Thanks, Alexandra. Waka Guyana Dailuchi Huinga Aka Carl Hill Was Manyak Igiaga Gamumuma. I'm speaking Alex's language. I'm actually part Dina Athabascan, so I know more Yupik than I do Athabascan though. Thank you for coming and listening to this presentation today. I'll get right into it. Alexandra talked about the planning process and how long of a haul that was, and just deploying this device has also been a long haul. All of the components that you see there were trucked and shipped from Maine to Homer, Alaska, where they're put on trailers and a barge brought over to Williamsport, where they go over a 13-mile mountain pass portage road and into the eastern part of Iliamna Lake, where they're put onto another barge and barged for another 90 miles or so down to our village of Igiagik. So everything has to be truckable, and we have to be able to disassemble it and reassemble it. All of the equipment that we have locally has to be sufficient to do this, and we are lucky that we do have a construction company that owns a fair amount of equipment and a modular barge. So we are lucky in that respect. And we can go to the next slide, please. So this is, you saw this in the aerial footage, but this kind of labels, the sites that we use for deployment of our system. The assembly area is the area that we offload and load barges that come from the other end of the lake. And I'll also throw in there that in addition to the route that we have to travel, that's only available around 4 or 5 months of the summer. So we're basically cut off from any of that during the other months of the year. The main village of Igiagik you can see in the center of that photograph, and the runway is off to the left of it where we fly our fuel in. We have extended the road out to another part of the area to build the future community on higher ground. I do appreciate what the Quinault folks are having to go through. We have some villages in Alaska doing the same thing, maybe on a bit of a smaller scale. The Kwijak River flows out of Lake Iliamna right in this picture, and you get if you can stand on the edge of the river and look across, you get a great visual on how much water is flowing by there every day. We drink the water right out of the river. We're very concerned about our water quality, and not only for drinking purposes, but for the fish that run through our village. In the lower left, you can see some of the support vessels that we use for deploying the device, a safety vessel and a work vessel. In the lower right, you see our excavators launching the device. We can go to the next slide. So the next phase for us, since we've proven that we can generate power with the RivGen device, solar and wind, is to tie it all into our diesel generation system. We are the power company in Igiagik. We don't have any other sources of power coming in from other power plants, so we're dependent on our diesel generators and nothing else. So to integrate these into our diesel generator system is extremely important and a key piece to this puzzle. We can go to the next slide. I'm sorry, there's a little bit of a delay on my end, but I put this graphic up not to go through it in detail, but to kind of describe the complexity of integrating these devices. We're challenged, like many of the 250 villages that Alexandra talked about, we're challenged to just maintain and run our local power plant with 365 kW generators. We got a power plant upgrade that involves, automatic and manual switching of generators, and they come online by themselves. We're lucky to have a very experienced power plant operator, but every village in those 250 villages has to have a power plant operator, and they're varying levels of expertise and experience. So we do consider ourselves one of the lucky ones, but this is the key factor in being able to use the alternative energy sources that we're exploring. If we can't integrate them into our grid, they don't do us a whole lot of good. So this is, after we've developed helped to develop the technology to produce power, now we're starting to make decisions on how to integrate that into our existing diesel generator grid, which has to be our fallback. We have to be able to operate that system if these other devices fail. And we can go to the next slide. So this is another graphic that I wasn't expecting everybody to necessarily read through, but it's a matrix that we came up with in the decision-making process for our microgrid. There are a bunch of different tasks involved. And so we have quite a few contractors and support folks working on integrating these systems in order to not have overlap in funding or overlap in costs from different contractors. We had to get a real defined set of tasks and identify who is in charge of what task, so that we're all kind of playing from the same sheet of music and not duplicating funding efforts and things like that. And we can go to the next slide. And then I'll turn this over to Alexandra. She referred to me as the tech man, but I just want to say that we're all learning as we go. I'm not really the tech guy on this, but I do gravitate towards the technical side of things. I really appreciated the presentations from the other presenters. Jim, really, you taught us some things today, some terminology, and as isolated as we feel in with these COVID events in 2020, I'm feeling more isolated now that I've learned we are an isolated grid. So with that, I'll turn it over to Alexandra for some of the concluding thoughts.
So thank Guyana Carl. And I appreciate you speaking the Yupik on this platform here. Some concluding thoughts. Our teamwork has been key, and the teamwork is forever evolving. With this recent grant, we even have expanded our team to include legal advisors, utility consultants. What we're navigating is very unique in Alaska, and Alaska has a set of regulations, and so it's been, opening up a can of worms when it comes to the regulatory side and affecting the programs that are in place to incentivize diesel. So the teamwork with not only, and this expands beyond the hydrokinetic company. What I appreciate most about our project is everyone has appreciated, or everyone has done to their best ability to honor what the wishes of the community are, which is not to be single focused on one type of resource. So the hydro people are talking to the wind people, and together they're looking at our grid, they're looking at our distribution, they're looking at the biggest consumers of it. So together they're looking at an integrated approach beyond diesels, just alternatives in general. So the teamwork, I think has been not only key, but it's bringing us to the point where in a year from now, we will really need to sit down as a community and think about the ownership structure around this new power source. We've owned our utility, we've owned our diesel. There comes the risk and benefits of owning this alternative energy, and looking at different structures and how might our village invest in this for the long term if it proves itself further. The other thing that was shocking to me as a community leader, I thought, oh, 1.5 million, I was very naively, I thought $1.5 million will get our diesel upgrade. We worked so hard for that. Okay, we got the diesel upgrade. It's already been 10 years. It needs another upgrade. Okay, where did that come from? Like, why wasn't I even aware of that? And now we need to put a schedule of upgrades as something that our community needs to set aside funds for. Secondly, I thought eventually they would just go away. If we're planning to go diesels off, they would just go away. I'm finding out now, and everybody on the line already knew. So I'm just coming to the party late. The diesels are here to stay for I don't know if we call this the interim or the long term or what, but they have to be primed and ready to come online at any given moment. So they need continual upgrades too. And the diesel market continues to be difficult, but they're here to stay for this time period we're in. So before 10 years ago, when we were getting these upgrades, I thought, well, eventually this will go away. But actually, I need to keep bringing funding online. We need to keep bringing funding online to keep them able to integrate and primed and ready to turn on if and when these diesels or battery energy storage system Carl talked about fail. Then there's the whole navigating state policies and programs. And then not only that, we're sitting up, like I said, about the largest salmon run. We have proved that in adult salmon do not interfere with the device, but out-migrating smolt, local indigenous knowledge tells us that they will not be impacted by this device, but we absolutely cannot and will not go forward if it affects the smolt migration. When we showed that picture of Igiagig being the headwaters of the Kwijak River, it is, the entire Bristol Bay salmon run comes out of that throat. Igiagig in the Yupik language means like water down the throat. It is the throat, and it is the only out-migration and in-migration of salmon, of which we are totally dependent on. So we have yet to solve that little last piece of the puzzle, and we're working on that for this coming May. And lastly, it's just growing our own local capacity. Like I said, we're 70 people. We're lucky that Carl comes from an engineering background, is able to operate and manage our locally owned construction company. But these are our commercial fishermen are our boat drivers and equipment operators, and it's very important that we have the capacity to run this system on the day-to-day. And you can go to the last slide. That's basically it. That's going to be an ongoing challenge, I think, for any organization, but I recognize we're way over limits. So turning it back to you, James.
No problem, Alexandra. Excellent presentation, and what an amazing project and challenge, and I admire your guys' leadership and persistence in moving that project forward over the years, and I'm excited to see how it continues to progress and as you said, there's probably not necessarily an endpoint, but a continual evolution of the power supply there. Really, really cool stuff. So with that, let's get to questions. Well, we do have quite a few questions, so that's great. If the audience has any additional questions as we continue to talk, please do submit them in the written format, and we'll try to get to as many as we can. Just going to work my way down the list. First question here is probably a Jim Riley question, but it's what are the opportunities to smooth out PV output and other non-dispatchable generation, capacitors, or other sorts of battery storage. Can you touch on that a little bit?
Yeah, so I think it was mentioned in the question, battery storage and things like that is definitely one way to do it, and that can battery storage can help smooth out PV and wind variability at different time scales. It can be on the second to like 5-second time scale. It can capture some of those variations. It could also shift it out over a couple of hours. There's also a number of ways that have been done and are being implemented in various areas to smooth it out so if you have a 10 megawatt array, for example, you could curtail it down to approximately 7 megawatts, and then it gives you a little bit of headroom above what you're using, that 7. So you have sort of some headroom between 7 and 10 megawatts, for example, just throwing numbers out there, but so that you can use that to dispatch up a little bit. So it's easier to control any ramp up or down that's coming from a cloud. It's easier to control a ramp up because you can control like the output of the inverter, but it's harder to control as a cloud starts coming over. It's harder to control that way down. So by doing what I said, like the curtailing, that's one way of sort of smoothing that decrease in output from any variability that's coming. But yeah, there are investigations of supercapacitors coupled with energy storage and things like that. There's also some inherent storage within the inverters themselves. A lot of inverters have inverters and other things like that, or have capacitors and things like that built into them to try to help smooth it. But yeah, energy storage and also just managing the PV through like meaningful, purposeful curtailment are two of like the primary ways that are done to try to manage variability.
Great, thanks, Jim. A similar question, building on that, can you talk about storage and its roles in terms of duration, like opportunities for either seasonal storage or transient variability in production versus peak shaving, kind of the different high-level storage, maybe not even technologies, but just the opportunities for fulfilling those different needs with storage?
Sure. I'll try to pull. So I can't remember who produced it, but there was a great graphic that talks through different types of energy storage and where their really sweet spot is. And a couple of the examples you'd mentioned. So longer duration energy storage, something like seasonally, is definitely more leans into like pump storage, hydropower. There's compressed air energy storage, a number of things like that, where you're taking up a massive volume and you're sort of storing a large amount of mechanical energy. There's also, and I'll move from sort of long duration storage towards really short duration sort of capacitor type storage, which just like instant between milliseconds and multiple seconds. That's sort of the time frame where they play. But yeah, so it's pump storage and compressed air energy storage are sort of longer duration, but they can play in the shorter duration areas as well. And then as you move down the line, you get to things like flow batteries, which sort of use 2 tanks and a chemical reaction between the 2 tanks to produce and store electricity. That's largely how a flow battery operates, and you're moving a fluid from one side to another and positive or negatively charging that fluid so that you can extract the power later. And then you move towards things like lithium ion batteries, which are fairly quick, or then you move towards lead acid batteries, which is sort of a liquid or a gel that is like transferring from one side of a plate to another. And that's getting fairly quick, and that sort of operates in the dynamic, like really quick time steps, but is also used for hours and days worth of storage, probably hours worth of storage typically. And then lithium ion can do the same thing. It's very energy dense, but it can play in the extremely fast space, but also is used for that minute to hour, sometimes to daily energy storage. And then getting even faster than that, we go into the space of things like energy or capacitors, and there's batteries like lithium ion, lead acid batteries that are coupled with capacitors or supercapacitors to try to make them capable of responding really quickly. And when I say quickly, everybody has a different time frame in mind, but it's sort of on like the sub cycle, which is more than 60 times a second. I think that might have, I think that answered the question, hopefully.
Yeah, that was great and very detailed. We'll have you on for our next energy storage presentation as well. just teasing. Another question here, and this one is for Kelsey. What are the plans for the current village site, the lower site, as you succeed in moving up to higher ground? Is there any energy generation opportunities down there, either wind or and then in the water as well? Is there energy generation, either hydrokinetic in the river or tidal or wave?
So we don't have plans yet for the lower village. No one's being forced to move, so odds are there'll be people down there for a while, which may make it hard to do anything large scale. Ideally, I think that would be sports fields, garden, for food production, or potentially it would be great to get that back to some estuary habitat for fish. So we haven't done any planning for that. The first thing that has to happen is we actually have to get people out, and that's a big enough effort in itself. So, and we have not really looked at energy production in the lower village. I mean, depends where you are in the lower village, whether say solar might work or not, just because of trees. Got nice tall trees there on the Olympic Peninsula. And I think we would want to keep most of our, or all of our energy production out of the tsunami zone. And so that would rule out the lower village. Doing stuff in the ocean or in the river could be sort of difficult, A, with the tsunami, and then B, just because of the sensitivity for fishing. Anything in the river would have to be very, very carefully done, and there would have to be assurances that no fish could be affected at all adversely. So I think that would be very difficult. I'm not sure if the river has enough flow to use the same device as they're using there in Alaska. And in the ocean, if we're away from the village, maybe. But anything near the mouth of the river, I think, would be somewhat problematic in terms of using wave power or whatever. We haven't really looked at that. There's been, I guess, initial studies done years ago looking at that, but I don't necessarily foresee those power sources in the lower village or in the ocean river.
Gotcha. Thanks. We had a question on the population for the Quinault village. I think it was 650. You can correct me if I'm wrong. We also had a question about your timing.
650 folks in the lower village, 820 overall. There are some houses that are up the hill. That wasn't done as an effort to get out of the tsunami zone or anything. That was done before really the realization of the tsunami danger and climate change. In terms of timing, well, we've got the first building just about done. It'll be done in December. I have engineering plans done for the first neighborhood of 60 homes. We don't have funding for that, but we've got plans for it. We're working on plans now for a fire station, one in Tahola, one in Queets, and one in another place. And the BIA is working with us on a detention facility, not a police station, but a detention facility. So that would have to require a police station coming up pretty soon after that. We're working on museum plans and a recreation building plan. So we got a lot of buildings underway in terms of at least feasibility studies, if not actual plans. The question is going to be funding, and that's a lot of buildings. That's expensive, even if we get grants for everything. But getting grants for all of it is going to be difficult. There's no real great fit for getting a lot of construction done. Most construction grants are very competitive. So, and what the folks look for at agencies isn't necessarily the data that we can provide them. If you look at Department of Transportation, a lot of that's based on accident data or freight speed. We're just trying to build neighborhood roads that normally would be handled by the private sector off-res, but it is either the Department of Transportation for roads or HUD, but then HUD has affordability strings. So there's no, I guess, clearinghouse. There's no one way to get stuff funded, or a lot of things funded all at once. And even if we got stuff funded all at once, it would be a large outlay from the nation with the match funds for doing 6 or 7 buildings. The first building cost $15 million. Now it's one of the larger buildings, but still that's a significant cost, which the nation bore itself. So, So in terms of timing, it's all funding related. We've got plans ready to go. It could start more in an earnest right now, and then we can continue with other plans or finalizing other plans for new neighborhoods or museum, et cetera. So it'll be a 10, 20-year process.
Gotcha. Yep. Yeah. Well, you've started with the planning, which is good, rather than just jumping into doing stuff. So I think that gives you a roadmap, hopefully.
Yes.
We have a few questions here related to the Geogix project. What's the capacity of the RivGen units, and what's the speed of the river flow?
I guess I can take that. This is Carl. The current device is rated for 35 kW, and we intend to have 2 devices in tandem, which should carry the load for the village. I think our peak load is generally in the low 60s, if I recall correctly. So we require a pretty small amount of energy. I think the river, when it's flowing at its peak, is around 7 knots of current.
Okay, and that river flows year-round. And how do you maintain it? How do you maintain the unit while it's deployed?
So the river does flow year-round. The flow goes down when the ice starts to cover the lake. We do get the entire lake gets covered in several feet of ice most winters, so we do have a reduction in flow. So we're not able to do anything to the device in the winter. There's no way to access it with vessels. It would be too dangerous in the ice conditions. We do bring it up in the spring and throughout the summer for maintenance events, and so that's done it's ballasted with water in those large pontoons to the bottom of the river, and we go and retrieve the umbilical and pump air into each of the pontoons and bring up one pontoon at a time and bring it to the surface for maintenance.
Gotcha. Talking about your planning in Geogix, have you or consultants used any modeling tools or resources like DOE's SLOPE platform? It stands for State and Local Planning for Energy, and has that helped inform your decisions?
I'm not sure which models we've used, and maybe Alex, you remember, but that we have done some modeling, especially on the ORPC side. I'm not sure if they're DOE specific models. Name that pops up is the Homer model. I don't know if that's the correct one or if I'm thinking of a different subject, but we have used modeling extensively.
Thanks. Yeah, Homer's probably one of the models. Great. Well, that puts us just past our time, so I think we're going to cut off our questions. Let's wrap up here. I appreciate everybody's participation today. An excellent slate of presentations. And there was a question about the trying to watch that video. If you go to the slide deck, which the link for the slide decks, which are posted on the internet, was provided in the chat, and you should also get an email about it. If you go to the slide deck, you can, I find the URL for the video and play it at your leisure. Apologize for the issues on the audio there. Sorry,
I think we've lost. Oh, James is back. I was hopping in.
Now realized. Sorry, I was on mute. Thanks, everybody. We got our final webinar here posted on December 2nd. It's modified from its original December 9th time. Please join us for that. Thanks to all of our presenters today and to our audience for your time and participation. And with that, we're done for the day. Have a good day. Good day.